Okay, so I suppose I'll start the session today. So I welcome the viewers to this problem solving and live interaction session for the subject engineering mechanics. So which is being offered by Professor K. Ramesh in the Swayam portal. So today we will be looking at problems from week 7, which has to do a bit with belt friction and then the starting of dynamics, including particle dynamics and circular motion. So let us look at the first problem. It says a tree surgeon weighing 75 kgs a tree surgeon weighing 75 kgs is trying to come down a branch using a massless rope tied around a branch as shown. So we can see that the tree surgeon is there, and then it is known that he is trying to come down. He or she is trying to come down the tree with the help of a massless rope. Considering the lap angle to be 180 and mu to be 0.1 for simplicity, what is the maximum force that he must, what is the minimum force that he must exert on the rope to gradually move downwards is what is asked. So let us in fact isolate this and draw the free body diagram. So let me copy this and put it here. And then we have the tree like that. So I have essentially split this into two parts. And then I'm just analyzing the tension in the table. So given that the tree branch is offering some friction, naturally the tension will not be same on either side of the ropes. So one side it will be more, and friction and the other side's tension will counter it to keep it in equilibrium. Okay, so we have two tensions here. One is from this rope and the other is from, we use a different color. One is from this, and from Newton's third law, equal and opposite. Okay, and then to complete, in the interest of completing the free body diagram of the tree, we can see that many other concepts also get involved here. For example, if we look at this branch, it is almost like a cantilever beam where a point load is applied at the location of the rope. The point load is applied. So in a way, to complete the free body diagram of the tree branch, there will be some shear force and bending moment, which we are not worrying about right now, but nonetheless it will be there in order to counter the loads. But since this is not of our interest, we will look at the person's free body diagram. Okay, so we have two tensions, and then we have the mass of the person here as mg, and we have been told that the rope is massless and so on. Okay, now we can clearly see from this image, we can clearly see that this is the rope. We can clearly see that this is the rope that the person is actually holding, that the tree surgeon is actually holding, and this is the rope that is connected to the seating mechanism, or the cloth or rug over which he or she is sitting to come down. So essentially this is carrying the entire weight, entire load downwards, and he is holding this in order to prevent him from falling down, but instead he is just applying minimum load to keep his acceleration to a minimum so as to slowly come down. So in that case, we can clearly see that this is T2 and this is T1. So from Newton's third law, appropriately this is T2 and this is T2 and that is T1. So the entire concept about belt friction is that we should be able to identify T2 and T1 correctly. Once that is identified, it's just a matter of substitution. So we know in belt friction that T2 by T1, or the higher greater tension by the lesser tension, is given by mu theta, where theta is the angle of lap angle in radian. Now we can see easily that this is invariably a positive quantity and greater than 1. So the minimum value that can go to is 1. When it will go to 1? When either theta is 0, which implies that there is no lap, so essentially everything is straight, or if there is no friction, T2 will be equal to T1. which is essentially the case where when we have been discussing a frictionless pulley. In such cases, mu is 0 because we are considering it to be frictionless when T2 becomes equal to T1. So that is just a degenerate case of this condition. Okay, now we know that the man or woman is trying to climb down slowly. So we can apply the equilibrium conditions here. So let me take this to be the x direction. Let me take that to be the y direction. Now sigma x equaling 0 is 0 equaling 0, which is not helpful in any way. So let me apply sigma f y equaling 0. That gives me T2 plus T1 equals mg. This is the first equation I get. So this is the first equation I have got. And then I also know another relation which relates our T2 to T1 because belt friction is in play. Now here theta it is actually given that the angle of lap is 180 degrees. So we will take that equally. So theta here is 180 degrees, which implies 180 pi by 180, which implies pi radian, and mu is given to be 0.1. So we will directly take that. So what does the second equation give us? T2 is nothing but T1 e power mu theta. So we can substitute this in that equation. So what will we get? T1 into e power mu theta plus 1 is nothing but mg, where m is the mass of that person. So from here T1, in fact T1 is what we have been asked. If we see, T1 is the tension that the person is applying. T1 is the tension that the person is applying here. T1 is the tension that the person is applying here. So that is what we have been asked. So T1 is nothing but mg by 1 plus e power pi into 0.1. So let me bring this here. Let me duplicate it, or rather, let me not do that. Okay, so T1 is given by mg upon 1 plus e power 0.1 pi. So can we substitute and find this out? It can be done easily. 0.1 pi. So this comes out to be m is 75 kg. So it is 75 into 9.81 divided by 1 plus e power 0.1 pi, which comes to 310. So this comes to 310.56 Newton. So we have our answer here. So this is the minimum load or force he has to apply, the person, he or she has to apply in order to prevent from falling, which comes to around 30 kgs. Very well. So this is one example of belt friction which we saw. So similarly, let us move on to the next problem. So it is given that a truck and a car are moving towards each other. So the truck is moving like that, the car is moving like that. Okay, with constant velocity. So this is key. So it is given that the velocity is constant when both the drivers saw the other and immediately applied the brakes. So since we know that once we apply the brake, it is not that there will be a dead stop here. Since this is carrying some momentum, essentially this has to come to zero after traveling some distance. Same goes for the car also. So the coefficient of friction between all the tires and the road is given to be 0.18. Okay, and the vehicles were at a distance of 230 meters. So when they saw each other, when both the drivers first applied the brakes. So essentially the distance when they saw each other and started application of the brake was 230 meters. Of course, there will be some more things to it, but for the sake of brevity and simplicity, the solution, the question has been posed this way. So there is 230 meters in between them. Mu is given to be 0.18. Okay. Given that the vehicle just managed to prevent a head-on collision, and the truck was initially moving at 55 kmph. So this was initially moving to the right with 55 kmph. What was the initial speed of this vehicle? And what is the constraint given here? That they just managed to prevent the head-on collision. What does that mean? Essentially, in terms, this means that this car, it got to some point here, and this truck, it got to a point where they just, so we will consider it this way, that they just touched, just managed to come over each other and prevented their collision. So it was something like this. This is the instant at which they stopped. Naturally, it will be a little more than this, but to understand the purpose behind the question, we will consider it to be this. Okay. So now we have been told that they are moving with constant velocities and then they applied the brakes. So let us see what happens when they apply the brake. So let us take this to be the tire, and then there is some mass that is acting. Take it mg, and then we know that the road will apply a normal force N, and let us take it that it is moving to the right. So friction is trying to oppose this. So I'll take it that this is essentially mu mu N in the limiting condition, and the entire thing is getting decelerated. Essentially, it is getting decelerated by some acceleration in the opposite direction. So I'll consider that to be A. So the entire system, this wheel system is actually undergoing a deceleration of A. So I'm just putting deceleration in the opposite direction. Okay. Now if I take the sum sigma f y equals 0, that is indeed 0. The tire is not going through the floor. So this is still holding. So this gives me mg equal to n. Now sigma fx, if I see, this is not equal to 0, but I have some, this is, if this is of mass m, so ma will be my acceleration that is acting in this direction. So I can see that only one force is acting in that direction. So what this implies is ma is acting in that direction. So I have minus mu n equal to minus ma. But n is nothing but mg, so it is giving minus mu mg equal to minus ma, or acceleration is nothing but mu g in such a case. Okay, so we have derived what acceleration is, what the deceleration of each of these vehicles are. Now let us apply this. We take it that the force has been applied, there is no other force, so essentially the acceleration is constant. So what is happening is the total distance traveled is 230 meters. So for this vehicle, we know what is the distance traveled. When there is a constant deceleration of mu g, we know what is the distance traveled. Now we can get this from, in fact, let us first derive the equations of motion here. Okay. So essentially what happens when there is a constant acceleration is what we are trying to see here. When acceleration is constant. So let us see what happens. Now we know that acceleration vector is nothing but velocity time derivative of the velocity vector. Now if for each and every coordinate system there are three independent coordinates, so let us consider one coordinate. This is a vector equation. Now considering x direction for say. Now let me consider the x components of this. So essentially ax is nothing but dvx by dt, where vx and ax are just scalar components in the x direction. So for simplicity, I will drop the subscripts here. So dropping the subscripts, I get a is nothing but dv by dt. And mind you, this a is constant. That is the premise with which we started. Okay, so therefore dv is nothing but a dt. Now let me integrate this. So I'll integrate this from some v naught to v at time t, whereas this will go from t naught to time t. So this will give me v at time t minus v at time t naught is equal to a. I can pull out since this is a constant acceleration. That is why I pull this out. That is the entire basis of a into t minus t naught. So say I set my time or time reference, the initial start from where I started making the measurements to be 0. Say t naught is equal to 0. Then I have velocity at time t is velocity at o plus a t. So this we would remember that this will go by many names. Vt, yeah, so this is coming. So essentially we have one equation of motion here for a constant acceleration case. Okay, now let us look at the other equation. Now we again know that this is nothing but dv by dt. Again considering the scalar components, I take this as dv by dt. Now this can also be written as dv by dx into dx by dt by inversion of the chain rule. And we know, now we have removed the time dependence, we know that dx by dt is nothing but v. Dx by dt is nothing but v in the first place. So therefore acceleration comes out to be v dv by dx. So far so good. So this will be a dx is equal to v dv. So integrating both sides again. So what will we get? Integrating from x naught to x at time t, from v naught to v at time t, we get acceleration into xt minus x naught is equal to vt v squared t minus v naught squared by 2. On simplifying this, if we define this to be s, the net displacement, say xt minus x naught is equal to s, which represents the net displacement, then we have vt squared is equal to v naught squared plus 2a s. So this is how we get the second equation of motion. So we have got two equations of motion. Similarly, now we can define v to be dx by dt. So on cross multiplying, I can see that it is nothing but v dt equaling dx. Now mind you, I have not said that v is constant. V is necessarily a function of time if a acceleration is constant. We know that v at any time t is nothing but v naught plus a t. So therefore dx is nothing but v naught plus a t dt. So now integrating this from x naught to xt dx gives us v naught plus at integration dt from t naught to t, t naught to t essentially. So what does this give us? Xt minus x naught gives us v naught into t minus t naught plus half a t minus t naught the whole square. Say xt minus x naught, we set it as s, and we take our initial time reference to be 0. Then we get this as s is v naught t plus half at squared. So this is the third equation of motion we have got. So we should keep this in mind that these equations of motion, as we have seen with the premise with which we have derived, that these are only applicable for a constant acceleration case. Okay, very well. Now coming back to the problem, we have been told that this truck is traveling with some velocity and this is traveling with some other velocity, and both are moving towards each other. And we know what is the deceleration each of them is experiencing, which is equal to mu g, which is constant. In such a case, can we calculate the distance traveled by the truck? Hence, I'll just take this image, copy this. So what this gives us is, in such a case, I have this equation that s of the truck plus s, or rather magnitude of s plus magnitude of that by the car is equal to 230 meters to just prevent collision. I take this equation of motion and put it here. Now for velocity of at time t, essentially when the time taken to stop the truck, vt is nothing but 0. So therefore v naught squared plus 2as is nothing but 0. Therefore s is nothing but v naught squared by 2a. This is because it has stopped. Okay, but we know that a is nothing but minus mu g, because it is decelerating. So therefore s is nothing but v naught squared by 2 mu g. So this is how we will calculate the distance traveled by each vehicle. So this is the distance traveled by each vehicle. So this is distance traveled by each vehicle. In such a case, for the truck, V naught is given to be 55 kilometers per hour, which is nothing but 55 into 1000 by 3600 meters per second. Since g we will be substituting it in meters per second, in order to have it consistent, we need to substitute this in meters per second. So this comes out to be 15.228 meters per second. Let VCR be V naught for the car. So therefore, by 2 mu g plus v naught car by 2 mu g is equal to 230 meters. So this is what we get. So if we substitute this, P naught for the car is nothing but 230 minus this quantity, this entire thing into 2 mu g. So this will come out to be V naught for the car is nothing but 230 into 2 mu g minus V naught for the truck. So this is 230 into 2 into 0.18 into 9.81 minus V naught for the truck. We just got it to be 15.28. So therefore V naught for the car is nothing but 230 into 2. Oh, I'm sorry, I forgot the squared. So this should be squared. This is also squared. Yeah. So this is 230 into 2 into 0.18 into 9.81 minus 15.28 squared and under root of that. So this comes to 24.06 meters per second. Now if we look at our question, it is asking us to report the quantity in kmph. So essentially we can just convert it back, which comes to into 3600 by 1000, which comes to 86.63 kilometers per hour. So this is the initial velocity of the car in the opposite direction. So this comes to 86.63. In order to just prevent collision. Okay, so let us look at the next question. So this question gives us an application of the previous question gave us an appreciation of the application of the equations of motion derived in the case of a constant acceleration. Okay, so let us look at this question. As a result of monitoring scribed lines C and D, so there is a body, and then we have two scribed lines on that. So one of the scribed lines is C, the other line is D on a rigid disk from a fixed reference. So we are monitoring these scribed lines from a fixed reference, which are scribed on this rigid disk. It is found that the disk rotates in the clockwise direction. So that is what is found. That is the inference we have made. So identify the correct relations that support this observation is what is asked. Relation or more than one. Relation or relations. Okay. So first let us replicate this. So I have a disk like that. I have the line D like that. And then I have another line. I have another line drawn like that. That is line C. Okay. Now if I were to extend this, so let this be the fixed reference. And then I have this line here. And then I have this line extended onto the fixed reference. So let me draw this as a dotted line. Let me also draw this as a dotted line. So this is the case we are dealing with currently. So what is given is this is theta. I have this to be beta, the angle between those two lines is given to be beta. Let's erase this out. And this is given to be phi. So this is what we have as of now. Now it is given that it is rotating in the counterclockwise direction. So let us make a copy of this and then let it rotate like that. Let us say that it has rotated like that, but not the reference. The reference needs to be straight still because it is a fixed reference. So I'll bring it here. Okay. Now let me move this reference. Essentially what I have done is I'll erase this. Let me erase this and bring back the reference here. So it has moved like that after some time. Now the question is whether I extend it to the fixed reference. I extend this also to the fixed reference. Now again, after that time t, this is my phi now. This is theta now. And this still happens to be beta. Now I can see that once this has rotated t at t plus some delta t. I can see that once it has rotated in the clock, rotated this way, these are the angles from the fixed reference I'm observing. So I can see that theta was initially more, which became less now. And as for phi, phi was actually more and it has become greater now. If this was some 60°, it has become greater than 60 upon rotation. So essentially the nature of this and the nature of this is opposite. So if I take this to be positive, then naturally phi has to be negative. In the same, as a consequence of this, if theta dot meaning theta dot is nothing but d theta by dt. If this angle is increasing as a is decreasing as a result of increment of time, if theta happens to be decreasing with time and phi happens to be increasing with time, naturally theta dot will decrease with time and phi dot will increase with time. And this is omega. So we can see that theta dot is minus of phi dot. And we can see that when this is rotating in this direction, theta is actually decreasing. So we know that counterclockwise omega is negative, which is equal to omega. So I have got this relation here. Okay. We also can see that the line between this is the line between two rigid bodies. Since this is a rigid body, therefore beta dot is 0. So we have one of the answers here and the other answers here. So these two are consistent with our observations. Okay, so now that we have derived the equations of motion, let me just put them in one place. I have this equation here. Let me copy it. I have this as one equation. Then I have this. And this is the third equation. So I have this as equations of motion. or constant acceleration. We should never forget that. Okay. So this question says a bowler throws a full toss, meaning it did not bounce, it directly went to the bat, which was released horizontally with a speed of 130 kmph from a vertical distance of 2.2. So essentially, it was it had an initial horizontal velocity only. So it was released when this was perfectly 90 degrees is what the question says. So this V happens to be 130 kmph and this was released from a height of 2.2 meters. Okay. Consider that the batsman stands at a distance of 18.6 meters. So this distance is given to be 18.6. 18.6 ways to play this delivery. Answer the following question neglecting air resistance. So what we need to understand here is once the ball is here, it is given a horizontal velocity. As soon as it leaves the bowler's hand, it is in free fall. So at an instant, once it is launched, once it has lost contact with the hand, it no longer has a acceleration other than gravity. So to this ball, at the instant of release, essentially this ball has velocity in the horizontal direction, which is equal to 130 kmph. And this does not have any vertical velocity. There is no vertical velocity, but it does have free fall acceleration as g. So we know essentially this is a projectile. So therefore, this ball is a projectile. And we know that horizontal and vertical motions are independent of each other. So in horizontal direction, if I take this direction to be positive, and let me take this direction to be positive like that. So this is positive x and let this be positive y. So essentially my z is going into the plane of the paper. Fine. So I have acceleration in the x equal to 0, velocity in the x equal to 130 kmph. Similarly, in the vertical direction, I have ay equal to minus g. I have velocity initial in the vertical direction is 0 because it was released horizontally. So essentially this is 0. So in the vertical direction, I have ay equal to minus g and ay equal to 0 initially at the initial juncture. So now it is just a matter of applying these equations of motion. So let us see what the question asks. So this is what happens at the instant of release. So the question is asking, what is the time taken by the ball in seconds to reach the batsman from the instant it is released? So we know that the batsman stands at a distance of 18.6 meters in the horizontal direction. So therefore, Therefore, S is nothing but, we have this, I'll just copy paste this. I have this where S is 18.6 meters, V naught is nothing but 130 kmph, and acceleration is 0. So therefore, this is 18.6 is nothing but 130 into 5, 130 into 1000 by 3600 T, or the time comes out to be 0.515 seconds. So once the bowler releases the ball, it reaches the batsman within a time of 0.515 seconds. So that is the answer to this question. So let us copy and put it here. Okay. So let us look at the next question. What is the height h in meters from the ground at which the ball is thrown would pass the batsman? So essentially what they're asking is, this ball would have traversed like that when it is hit. So this is the distance that the projectile would have moved, and this is the distance h. So this is the path. Let me draw the path in some other color. So this is essentially the path taken by the projectile is what we are saying. Something like that. Okay, in such a case, we can see from the figure, let me move it here. Let me copy it and put this figure here. So what we are saying is h plus s in the vertical direction is nothing but 2.2 meters. But we know this equation. Therefore, s vertical is nothing but 0 minus half g t squared. Why 0? Because this had no initial velocity in the y direction, and the acceleration in the y direction is minus g. So that is why minus, and t. Now we know that these two are parameterized by t. So essentially the time taken by the ball to reach this place, to reach the batsman, at that same time it is falling like that. So t will be 0.515 seconds. So let me copy this and put it here. So therefore h plus minus 9.81 into 0.515 squared is nothing but 2.2 meters. So therefore h comes out to be 0.899, or similar to 0.9 meters. Now the question is asking, at the moment just after the release of the ball, the cricket ball has which of the following? Now we have already drawn it here. So let me take a copy of that and put it here. So this gives me at the instant just after release, is it having non-zero? It is having a free fall? Yes, because the only acceleration that is acting is the gravitational acceleration. It has zero velocity and non-zero acceleration. It has zero acceleration, non-zero velocity. We can see that the net velocity is non-zero and the net acceleration is also non-zero. So essentially, this is the correct answer. Okay, so let us look at this problem. A car is traveling on a circular road. So we have this as a circular road, and then this car is traveling on it. And the distance from where we are observing it, it is at a radial distance of 200 meters. And it subtends an angle theta like that. So this is angle theta with the x-axis. So we have been given the coordinate system x, y, and then this is at a radial distance of 200, which has subtended at angle theta. At the instant when theta is equal to 45 degrees is when we are talking, it is found that the car is speeding up with theta dot. If this is theta, then theta dot, it is given to be 0.2 and theta double dot is 0.1 radians per second squared, respectively. Answer the following questions for the instant depicted based on the given data is what is asked. Okay, so is theta, now there is a question, is theta dot the angular velocity of the car? The answer is a resounding no. If we were to treat the angular velocity of the car if we consider the car to be rotating, this is when the car is rotating. Such cases pertain to the car's rotation. And this will be about this point. Or rather, let me use a different color. About the green point. This is omega of the car. Not equal to theta dot. This is what happens when the car is rotating. Okay. So now let us look at what we have here. Now if this is R, it can be resolved into two components. So therefore, expressing the position in xy frame. So what will this come out to be? We have position vector of the car. Let us take this to be C. So RC with respect to O is my position vector, which is similar to RC, which is nothing but R cos theta I cap plus R sin theta j cap. So I have this here, and I have been given that theta equal to 45 degrees and R is equal to 200 meters. So therefore, RC is nothing but 200 cos 45 I cap plus 200 sin 45 j cap, which is, so RC is given as 141.42 I plus 141.42 J. So this is what we get here. So this is 141.42 X component, and then the Y component also comes out to be 141.42. Now it is asked The magnitude of the absolute instantaneous velocity of the car in meters per second is asked. Okay. Now if this is the position vector of the car, then velocity of the car which is Vc is nothing but drc by dt. Time rate of change of the position is nothing but velocity of the car. So Vc is nothing but d by dr of rc. What is rc? Rc is this. So we have this. Now what is I dot is equal to 0. I and j do not change, 0, or di cap by dt is 0. This does not change with time, whereas this is not the case in case of polar coordinates. Okay, so in such a case, Vc can be written as dr by dt cos theta I cap plus r d cos theta by dt I cap plus dr by dt sin theta So this we can write using product rule. But r dot, which is nothing but dr by dt, is equal to 0 since it's a circular curve. So therefore, what does this come out to be? Vc is nothing but this term plus this term. In other words, Vc is given as r theta dot I cap plus r in other words, Vc comes out to be minus r sin theta theta dot I cap plus r cos theta theta dot j cap. So I can further simplify this to be minus r theta dot. I can take r theta dot common. If I take r theta dot common, it gives me minus sin theta I cap plus cos theta j cap. Okay, so we have been asked the magnitude of the velocity. So magnitude of Vc is given as under root of r square theta dot squared into 1, which is nothing but r theta dot. So that comes out to be 200 into theta dot in the question is given to be. So from the question we know this. This is given in the question. So therefore this is nothing but 0.2. So this comes out to be 200 into 0.2, which is 40. Okay, Now similarly, let us write acceleration. So we have this as, or rather we have this as our velocity. So therefore acceleration should be by dt, which is nothing but d by dt of r theta dot into this quantity plus r theta dot into d by dt of this quantity again. So that is what it is. It is essentially alpha r plus omega squared r. That is what it will come to, but let us see how that comes. So essentially r, I can write this as, I'll replace d by dt with dot. D by dt of some a, I'll write it as a dot. Let me use that convention. So AC will come out to be r dot theta dot into minus sine theta I, or rather let me write it this way. So it will be r dot theta dot plus r theta double dot into this quantity, plus r theta dot into minus cos theta theta dot I minus sine theta theta dot j. So if I group all the I terms, this comes out as 2 r dot is 0 actually. So this quantity is 0. So therefore AC comes out to be r theta double dot sine theta I cap plus r theta double dot cos theta j cap minus r theta dot squared cos theta I minus r theta dot squared sine theta j. So my acceleration, what C comes out to be, if I group the I terms, it comes out as minus of r theta double dot sine theta plus r theta dot squared cos theta I plus r theta double dot cos theta minus r theta dot squared sine theta j. So acceleration of C is nothing but minus of r is 200 theta. Let me copy this. So I have this as the given data here. So it will be 200 into 0.1 into sine 45 plus 200 into 0.2 squared cos 45 I plus 200 into 0.1 cos 45 minus 200 into 0.2 squared sine 45. So acceleration of C comes out to be minus 19.8 789I 200 into 0.2 squared into sine 45. So this comes to plus 8.485 J cap. So therefore magnitude of this is nothing but 19.798. So this is 21.54 meters per second square. So this comes out to be absolute instantaneous velocity and absolute instantaneous acceleration come out to be 40 and 21.54 respectively. So this is 40 meters per second and this is 21.54 meters per second. Now we can see that how cumbersome it is when we express the velocities and accelerations in terms of x and y coordinates. We can see how cumbersome it becomes to differentiate this, which is why we go for a more elegant alternative of having it in polar coordinates. So I'll just show briefly the derivation if we were to represent this in polar coordinates. Instead of Cartesian, if we represented in polar coordinates, so in polar coordinates we have position vector, we have the position vector r given as r e r cap. Now we know that velocity vector is r dot. Essentially velocity is nothing but r vector dot, which is r dot er plus r er dot, and this term is not zero. This is not equal to zero, but rather it is equal to theta dot. Let me write it here. Actually, er theta is nothing but theta dot e theta, and e theta dot is nothing but minus theta dot er. Derivations are given in the lecture. So these are derived in the lecture. So therefore, velocity comes out to be the first term as it is r dot er cap plus r theta dot e theta. So this is my velocity. And then acceleration is nothing but velocity vector dot, which is r double dot er plus r dot er dot plus. Now here all the three variables have a time variation. So we will apply product rule. We will first differentiate one, keep the others constant, then differentiate the middle one, keep the first and third constant. Then towards the end, we'll differentiate this, keeping these two constant. So cyclically, we will apply the product rule. So this will be r dot. So this is r dot theta dot e theta plus r theta double dot e theta plus r theta dot e theta dot. So this comes out to be r double dot er, and we know this quantity is this. We have written it down, plus r dot theta dot e theta plus r dot theta dot e theta. We can see that these two terms are same, so they'll get added up, plus r theta double dot e theta minus r theta dot squared e r. How this came about? Because the time derivative of this is minus theta dot er. And these are derived in lecture. It can be derived trivially, but I'm refraining from doing that for the sake of brevity. So if I take er common, I have r double dot minus r theta dot squared er plus r theta double dot plus 2 r dot theta dot e theta. So this is the total term for acceleration in case of expressing it in cylindrical polar coordinates. Now we will later learn that this is actually the Coriolis component, which as we go about solving problems in rigid body for rigid body kinematics, we will find that this is nothing but the Coriolis component. This happens when there is radial acceleration. This is nothing but our centripetal acceleration, and this is our alpha r. So in case for circular motion, r dot equal to r double dot equal to 0. Therefore, for circular motion, acceleration comes out to be minus r theta dot squared er plus r theta double dot e theta. And we know that this is nothing but our tangential component, where this is centripetal, this is tangential. Acceleration. So we can see that once we actually represent the vector in cylindrical polar coordinates, then it becomes much easier to derive the equations of motion as opposed to what we did in x and y coordinates. So that was quite hard. And if you look at that question, it only had asked the position vector in terms of x and y components, while we went for acceleration and velocity and acceleration calculation, it had only asked the magnitude. So we need not have done this, but anyway, from first principles, we have derived everything. So I hope that will be beneficial. So this question is done. Okay, so let us look at this question. Now a centrally pivoted disk rotates in the clockwise direction. So I have a disk which is rotating in the clockwise direction initially. A massless inextensible brake band wraps around the rotating disk in order to bring the disk to a halt. The brake band is in turn connected to a massless rigid hinge. So essentially I have a lever like that, and then the brake band goes like that, and then it is connected to point C, which happens to be on a rigid bar which is hinged at E, and then I apply a force over there, to which a braking force F is applied. So because of the lever, I need to apply a lesser force in order to get a higher braking force delivered at the output. So answer the following questions is what is given. So let me just draw the body here. This is my disk. So this is rotating like that. And then I have the same So it gets magnified like that, and then I will remove this portion. Let this be the break band. So let this be the break band and let this be the disk. So let me put the disk here and the break band there. Okay, so it is like this. Now we have been asked some questions. So let us see what that is. Now we should know that this is a break band. So if the disk is rotating this way, for it to break, a force like that has to be applied. Since this is a break band, that is its purpose, so it applies a force like that. So this is the frictional force that the brake band applies to the disc. From Newton's third law, I can see that this is the force that the disc applies to the brake band. So once I know this, I can label this as T2 and this as T1, since T2 is invariably greater than T1. Okay. So which of the following are true about the frictional force applied on the brake band due to the braking action? So here we have been asked about the brake band. So we will see here on this free body diagram. So it is in the clockwise direction. So we can see that this is actually in the clockwise direction because of the braking action. So this is correct. So if one is correct, two cannot be correct. It is naturally not zero all over the contact length because it is applying a braking force. That is the entire purpose of the brake band. And it is acting tangentially to the band at every point. So if I take it here, it is applying like that. If I take it here, it is getting applied like that. So at all the points, it is tangential. So this is correct. In this question, these options are correct. Now let me take this and put it here. Now we are talking about the disk. Which of the following is true regarding the frictional force applied on the disk due to the braking actions? Now we know that this pivoted disk is initially rotating in the clockwise direction. So in order for it to stop, the braking force would have to be applied in the anti-clockwise direction. So naturally, this option is correct. And the last option says that it radially acts on the disk. We can see that if this is the disk, radially acting would imply this way. It is not radially acting, but it is actually tangentially acting at the normal to the surface drawn at each and every point. So if I have this disk like that, I have the normal to that surface drawn like that. So normal to that surface would imply that it is radial. If it is perpendicular to the normal, it would imply that it is tangential. So at each and every point over the contact length, over the lap length, the frictional force is getting applied onto the disc as a braking force in the counterclockwise direction or anti-clockwise direction. Okay, good. So now the question asks, given that the tension in the brake band segment is in brake band segment AD is 500, what when the brake is engaged, what is the magnitude of tension in the segment BC? So we have been, this is the segment AD, and we say that AD's tension is 500. So essentially this tension is 500. Tension here is what is asked. So we have been given T2. We have been asked what is T1. So this implies that T2 is 500 Newton. T1 is what we need to find. And from the question we can see that it is wrapped around like that. So therefore theta is equal to pi radians. Theta is pi and mu is given to be 0.1. So therefore T2 by T1 is nothing but e power 0.1 pi. Therefore T1 is nothing but 500 by e power 0.1 pi, which comes out to be e power 0.1 pi, which comes out to be 365, which comes out to be 365.2 Newton. Okay, now that we have T1, now let us draw the free body diagram of the lever. So I have the lever like that. This is my lever here. The tension in the cable, because if I draw the cable like that, cable is having a tension T1. So naturally it will apply a tension T1 onto the thing. And then what is this point? It is E. So therefore I have EY, and then I have EX, and then I apply the force P, or rather the force F. This is the force F. So this force is F. Now the free body diagram is complete. This is not part of the free body diagram of the lever, so I'll remove that. So this is my free body diagram of the lever, and this is in equilibrium. So what are these distances? This is 0.25 meters, and this is given to be 1 meter. Okay, so how many unknowns are there? Essentially, I don't know Ex, Ey, and F. T1 is known. T1 is known to be 365.2 Newton. So I want to find out what these quantities are. So sigma F equaling 0 gives me Ex equal to 0. Now sigma Y, Fy equaling 0 gives me Ey plus 365.2 minus F equals 0, or F equals Ey plus 365.2. So this is another equation. And then sigma moment, if I take it about E equal to 0, actually essentially this is the only thing I should be doing, because I want to calculate F. So in the exam, if F is asked, one is expected to gauge that they are supposed to take moment about E, so that they eliminate all the other unknowns in one go and directly get the force F. But for now I am solving for each and every unknown, so that it becomes clear. But one is expected to gauge how it will be asked in the exam and appropriately uh, choose the approach they want to apply. So this will create a clockwise moment. So this is minus F into 1 plus 0.25 plus 365.2 into 0.25 is equal to 0, or F is nothing but 365.2 into 0.25 by 1.25. So this force comes out to be 73.04 Newton. So I can see that I have to apply a much lesser load in order for me to bring that disc to a halt, as opposed to if there was no lever, I would be expected to apply T1. But since this lever is there, I'm able to apply a lesser force and still be able to magnify what is getting applied essentially. So my F is my input force. Input force is 73.04 Newton, and output braking force is nothing but 365.2 Newton. So this is what T1, this is what is getting applied, and T2 is manifesting because of the braking action. So therefore, mechanical advantage is nothing but output by input, which is nothing but so this will come out to be so with this system I need to apply 1/5 the force that is required as opposed to not having a lever at all. So that is my mechanical advantage in this case. So given that the tension, what is this come out to be? Tension in the portion, tension in the segment BC came out to be this, and then the applied force required comes out to be this quantity. It is 73.04 Newton. And then I have my mechanical advantage of this braking system is 5.0. So this is my mechanical advantage for this braking system. Okay, so now let us look at this question. The figure shows a driver pulley. The figure shows a driver pulley rotating in the clockwise direction. If the equation for the belt tension is derived such that T2 is greater than T1, select the correct representation of tensile and frictional forces on the belt is what is said. So we can see here this is a driver pulley, implies that this pulley drives the belt. So therefore force is applied since this is rotating like that, the driver pulley is rotating like that. What it will try to do is to take it tries to take the belt along with it. So this is the direction in which the friction will get applied. If friction is applied like that, then naturally this becomes T2 and this becomes T1 since T2 is greater than T1. So we can see that option B is indeed correct. If let us see if this was the driven pulley, then belt drives the pulley. So in such a case, I'll have a belt like that. It will have some tension naturally. It will have some tension. And then I have the pulley like that. So this will be my pulley. And let us say that this is rotating like that, which implies that the belt must have applied a force like that, which is why it is rotating. In such a case, my frictional force will get opposed. So this will be T2 and this will be T1. This is applied. And in this case, this is applied. So based on this, we can gauge in which direction we would be having frictional forces in case of a driven pulley, a driving pulley, and a brake band, as we saw. Okay, so let us look at this last problem for the day. Now it is given that this car, essentially both of them start from here, and then this car VA is traveling along this straight path with a velocity of A to be 12 meters per second and acceleration of A is 2 meters per second is what is given. So this is my point. Now B, a person at B driving the car is observing that the speedometer of the car appears to be constant at 9 meters per second. Now we know that speedometer basically measures the RPM and back calculates the speed of the car. So what it is essentially measuring is the velocity like that. So this comes out to be velocity of B is nothing but 9 meters per second, and this is constant. Now one thing we must immediately take note is that A is having motion along the straight line and B is having motion that way. So this is velocity of A and this is velocity of B. Okay, so for velocities, we know that if I have two vectors, one like that and the other one like that, let us say that this is VA and this is VB somewhere in space. In such a case, if I observe VA from B, essentially what I'll get is so I'll get velocity of A is velocity of B plus velocity of A with respect to B. Now let us look at this graphically. So what I have to see is, what I mean to say is that this, let me put it in some other color. So VB, when I add VB to some vector, it takes me to VA, is what I'm trying to say. So that vector which starts from here and takes it here, this is nothing but V of A with respect to B. This is how these two are equivalent. So therefore, I know from graphical approach, I know that this is how much? This is 30 degrees. Because if I draw a line here, if I draw a line there, I can see that this is 30. So therefore, this also has to be 30 degrees. Okay, and I know that this is normal. This is 90 degrees. This is 90. So I know that this is 30. I know this is 90, which is not the same 90 as that. So this is 90, which implies, what is this angle? This angle comes out to be 60 degrees. So now what the question asks is, what does B observe about A? So what can B observe? Essentially, velocity of A with respect to B and acceleration of A with respect to B. Both these quantities are asked. Both these quantities are asked. Okay, so from here I can see that using cosine rule, I can see that A with respect to B magnitude square is nothing but magnitude of VA, magnitude of VB minus 2 VA VB cos 60. So this I can clearly see. So what will this come out to be? This is equal to magnitude of VA in the question is given to be 12, and magnitude of VB, we can see that it is 9 here. So this means 12 squared plus 9 squared, 12 into 9 cos 60. So therefore velocity of A with respect to B, from here the magnitude of that comes out to be 10.82. Squared minus 2 into 12 into 9 into cos 60. So this is 10.8 second in this direction. In this direction. So as B moves away, as B moves this way, it appears that A is going that way. So as B moves, A appears to be moving that way. So this is velocity of A with respect to B. Okay. So same thing we can do for acceleration also. So let us do that. So for acceleration, from vector algebra, I know that acceleration of A is nothing but acceleration of B plus acceleration of A with respect to B. Graphically, how we will see this? I know that A is having a from the vector diagram, I know that A is having an acceleration is equal to 2 meters per second squared, which is given. It is given that it is speeding up like that. It is in that direction. Now we know that B sees the speedometer which is hovering at a constant 9. What this implies is this line is having no angular acceleration. So theta, if I took this to be theta, then theta dot I have theta double dot is equal to 0. However, since this path is moving in a circular, however, since the car is moving in a circular path, I will have a centripetal acceleration pointing like that. Now we have seen that centripetal acceleration is, if this is the path, let me draw the circular path here. Since this is the path and this is the car, so I'll have a centripetal acceleration like that. Which is equal to v squared by r. So this again, if I see, this is perpendicular to the velocity. This is my velocity, so this is 90 degrees. So this is 90 degrees. And I know that this angle is 30 degree. So I can make out that this angle is also 30 degrees. Which is equal to VB is 9 squared by, what is the R here? What is R here? It is 500. So it is 9 squared by 500, which is equal to 81 by 500, which is 0.162. So from here I can see that this is 2. This is acceleration of A. And then I have a vector like that, which represents acceleration of B. So this is acceleration of B, which has only a centripetal component. So let me put it like that. And this is perfectly horizontal. Now what I'm saying is, I add something to this vector which takes me there. So let me put that here. I have something to this vector which takes me there. So this is acceleration of A with respect to B. This is 30 degrees. So therefore, using cosine rule, I have acceleration of A with respect to b, the whole squared, is acceleration of a squared plus acceleration of b squared minus 2 a b cos 30. Minus 2 a b cos 30. So this is acceleration of a with respect to b squared is nothing but acceleration of a is given to be 2 meters per second, and acceleration of b, it came out to be 0.162. So it is just a matter of substitution. So let us substitute that. It is 2 squared plus 0.162 squared minus 2 to 0.162 into cos 30. So therefore acceleration of a with respect to b is so this comes out to be 1.86 meters per second squared. So essentially, if this happens to be the same, then that acceleration would appear to change the velocity in that direction, as seen from B. So that is what it is. This is how this problem can be solved using vector algebra or our vector diagrams. Now, once we have done and we are once we are confident with our particle dynamics, we will move to our rigid body dynamics with the constraint that the distance between one point and the other point on the rigid body does not change. So essentially, what we know about the distances when they don't change, now we have derived the equations here for a general case of particle motion with the frame attached to one of the points, and we are looking at the other point. Now if we apply one of the points, now if we consider one of the points to be on the rigid body and we look at some other point on the rigid body, then essentially the radial distance between those 2 points remains the same, in which case r dot and r double dot become 0. R dot and r double dot become 0 by virtue of that being a rigid body. In that case, we can see that it is a special case of our circular motion only, rigid body dynamics. So rigid body kinematics. And then towards the end, we will also see how to relate this to the kinetic quantities. So with that, we have solved quite a lot of problems today. We saw that how belt friction comes into play, and then we saw how the equations of motions are derived for the case of constant acceleration. It should be noted that these equations are only applicable when the acceleration is constant. And we can also have a rotational analog of the same kinematic quantities. Namely, this can also be represented in the rotational form, where V will become omega, A will become alpha, S will become theta essentially. So the same applies there also, provided that the angular acceleration is constant. Then we saw projectile motion, and then we saw how to scribe a line on a rigid body and note its angular velocities, followed by our example of a car that is going on a circular path, and then we are observing it from some point. What happens to be its velocity and acceleration we saw, and we clearly note that this theta dot, time rate of change of this theta dot, is not the angular velocity of the car. the angular velocity of the car would come into play in such a case, only in such a case where this car seems to be rotating about this green point in between. In which case, this car can no longer be treated as a particle as we have done now, and this would have to be treated as a rigid body. And we will see how to analyze these systems in the coming weeks. So, thank you. I'll close with this.